Okay, so we just talked about analyzing our variance into between treatments variance, our measure of treatment effect and error, and within treatments variance, just a measure of error only. Well, as I've mentioned to you before, again, every statistic has a symbol that represents it. So we had a Z, a chapter for Z statistics. We've had 3 chapters for T statistics. The number they use for, the letter they use for ANOVAs is the capital letter F. Remember, lowercase f would be frequency, so we want to make sure we're capitalizing properly for the symbols. Really, I'm guessing they picked that for the word factor. Otherwise, I don't know why they would have picked an F. It's the only thing that makes any sense to me, talking about factors using an F. So if we were using the language we normally use, we would call this an F statistic. Officially, it's called an F ratio. Whatever, F statistic, F ratio, but officially it's called a ratio. So picking up from right where we left off, what we said is what we're going to end up with in the top is our between treatments variance. Divided by our within treatments variance. That's what we're going to end up with when we finally get to our 4 steps in a while. Still, we're a little ways off of that yet. But when we finally get to our 4 steps and we get to step 3 for our math, that's basically what our last formula is going to look like. That's calculating our F statistic or our F ratio. Let me write this again, but in a slightly different way. Between treatments variance. We just said a moment ago that what that is comprised of is treatment effect and error. And we said we said within treatment variance is all error. So this has an implication for us. The error in the study is the error in the study. Doesn't matter where we write it, it's the same thing. So let's make up a number. Yeah. 5? Okay, we have 5 points of error. So let's think about that. Let's think about this now in terms of the null hypothesis. What does the null hypothesis always predict? 0 treatment effect. Null, 0. So the null hypothesis always says there won't be any differences. This treatment doesn't do anything. It is worth nothing. And the number we just made up for error was 5 points. Could have made up any number, right? Could have said 10, could have said 7.26. Whatever, but it'd be in both places. Well, what do we get if the null hypothesis is correct and there is no treatment effect? When we calculate our F ratio or F statistic, what we should end up with is a 1. Now that's different than our previous chapters. The null hypothesis has always predicted a T statistic or Z statistic value of 0. If there's no treatment effect, we should be at a 0. But for ANOVAs, because of the quirks of this math, if the null hypothesis is correct and there is no treatment effect, on average, we're expecting an F ratio of 1.00. And again, it's a statistic value, so it's always to hundredths place, whether it's a whole number or not, right? So this also has another implication for us. So first of all, the number we're expecting if the null is correct is different. It's moved from a 0 to a 1. The other thing that most of you are really going to like about this, ultimately, is that there is no longer any such thing as a one-tailed or two-tailed test. Not for ANOVAs. It'll come back in our last chapter. But because let's think about it. Variance is sums of squares divided by degrees of freedom. Sums of squares always has to be a positive number because it's squared values. And degrees of freedom based on sample size always have to be a positive number. So the numerator is always going to be positive and the denominator is always going to be positive. That means your F statistic or F ratio has to be positive. There are no numbers lower than 0 because it's always a positive divided by another positive. So it says also that the shape of our curve is going to change a little bit. Let me make space up here. So what we had been dealing with up to this point was a bell-shaped curve, right? Symmetrical, normal distribution. But now, because we can't get negatives, our distribution, our F distribution, is going to look like a skewed distribution. So the lowest we can get here now is 0. There are no negative values. And so they're all going to be positive values out to infinity. So there's no such thing as a two-tailed test. There is no left-hand tail. It's always to the right. So when we go through our steps, when we get to them in just a little bit, we're going to see that our critical region is only ever going to be in the right-hand tail when we look that up. We're still going to look that up in a table for step 2. Like always, the steps are basically the same. But F ratios, F statistics are always going to be positive. So again, only one-tailed tests for the next couple of weeks. So that is a breakdown of the overview of analysis of variance. Get the total variability for the whole study and then say what are those differences exist between the groups, which is treatment effect and error, and which of those differences, what are those differences like within the groups, which is only error, and then divide them. So that's where we're going to end up with this. So that finishes the introduction section of this chapter. In the coming series of videos, we're going to talk about the 4 steps, which really is kind of 5 steps here because we usually have some prep work to do. But like we have always done for these, we're going to talk through the steps conceptually first, and then we'll plug in examples and run examples. So we'll see you in the next video for starting to go through getting ready to run our hypothesis testing steps. See you in a bit.